He's hilarious. So we got the good closer here. Whenever you're ready.
Yeah. Okay.
All right.
Yeah!
That was terrifyingly enthusiastic. I think my only fear is that I gave this to you as a PDF, and so all my GIFs won't animate, but that's probably okay. Okay, so I guess in the realm of DFM adjacent topics, or DFM, but not quite for the M that you're thinking, let's talk about what to think about when maybe you build a small product and you would like to send it to a factory and make more of them. I guess the thing that I realized was that I learned a whole bunch of things really quickly when I needed to make a widget, and fortunately it wasn't my money that was being spent to teach me, but there were things that I didn't learn until I was at the factory and someone who knew better could teach me. So it seemed like there was an opportunity. There's an intersection between people who maybe build like little hardware and they're interested in productizing, and people who have knowledge about what to do with factories, and there's a gap there. Okay, cool. So who am I? If you run the command, I'm Borgel. I'm a firmware engineer, a consultant. In the last 4 years, I've worked on about 20 projects. 6 of them went to production. Some of those companies are even still alive. On the internet, I go by Borgel. You may know me from the one hit, I make DEF CON badges. This is last year's. My level of experience is somewhere between my friend's constantly terrified baby and 2 Gandalfs stacked on top of each other. I'm slightly to the left of the center, so read that as you may. Okay, so some guardrails. This information is relevant based on my experience. I would suspect it's only relevant for small to medium type volume manufacturing. If you work for Apple, it's not going to look like this. Dealing with small manufacturers is not the same as dealing with big manufacturers. It's not going to look like this. This is sort of, in my experience, for like hundreds, thousands, tens of thousands type quantities, not millions. If you're here and you're expecting to learn from this and then you're expecting to go put the Galaxy S10 into production, you're fucked. So hopefully this is fine. So I guess let's, yeah, that was the Note 7, yeah. Smaller batteries, less close to the sun. Okay, so did I lose my mic? Boop, 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 boop. Okay, cool. So what does a factory do? If we start at the beginning, a factory builds your product. Yeah, you'll be in this soon. Let me ask your permission. Okay, great, he nodded. Okay, so a factory builds your product, that's cool. Oh, it's animated. The guys that did Cards Against Humanity put together like a product fulfillment company called Black Box. This is from the top of their homepage, and it's friggin' awesome. So that's a factory builds a product that looks like that. Okay, so factories build your product. That's cool. They do some other things depending on the level of complexity and your money you're spending and all that. Maybe they help you get things ready for manufacturing. Maybe they help you build some of the parts. Maybe they build all the parts. Maybe they build none of the parts. They just stick them together. They can do some stuff to ensure like quality of the things coming in and out. Maybe they package your widget. Maybe they package your widget and put it on a pallet and ship it. Maybe they don't. A factory is sort of fundamentally a machine. It's a machine made of meaty humans. Here are some humans. It's designed basically to do one process fundamentally. You're the one who defines the process, but it's designed to run that process, and it's designed to run only that process. And when everything works well, the factory will do exactly what you told them to do and exactly nothing else. Taking initiative is helpful in some places, but this is one of the places where you don't want people to do things besides exactly what you want. So that raises an interesting problem. Someone is going to do a quality check on your product, and God, hopefully it's not your customer. And so if it's not going to be your customer, that means it has to be you. So remember, the factory will do exactly what you tell them to do, and they will do, hopefully, exactly nothing else. So unless you specify, for instance, when you pick up the piece of plastic, if the piece of plastic is melted and brown instead of white, don't try to build a product with it. They'll, like, even if you, an engineer, can look at the widget and go like, wow, this is obviously broken, unless you give them some standard to use to decide whether or not it's broken, define a test of some sort, they're gonna try to use it. So how do you ensure quality? Well, there's a lot of reliable methods. You can use my friend Mike Choi here. You can see he's in the ESD smock, so he's official. You can use hope and prayer. That's a faith-based approach is a reliable option. Or you can test things, which is an option that I have some experience. Actually, I guess I've experienced with all these options in different varying amounts. But I recommend testing things. Okay, so testing or factory flow or how to test good. GIFs. So this is just like a super cheesy, like, here's a thing that a factory could do for a random widget. So there's like mechanical components like plastics. So maybe you get, so this is like stuff coming into the factory. So you get mechanical components, maybe they're like sub-assembled, and then assembled with some more like a gearbox or something you buy from someone else. You get PCBAs. You should test the PCBAs. Then they get like mixed together, and then you have like other, I don't know what a complex vendor module is, like an IMU that isn't one part, but it's like a whole board with firmware and a processor and everything that you're buying from someone else. So you do some sort of quality check, and like the factory integrates it, and like it's a pipeline or a tree or something. So imagine this. So where in here do you test? Okay, so there's a bunch of places. Hopefully your vendors are doing outgoing quality, but trust but verify. Don't trust your vendors. Your vendors are probably not doing outgoing quality, or their definition of quality is, oh, it fit in the packaging, so it's good to go. So you want to run some tests. This is sort of like our cheesy flow is like the archetypical circuit board in a plastic enclosure with a radio or whatever. It doesn't. So there are a few places based on something kind of that simple. One is what's called in-circuit test, which is the test you run on your PCBAs when they come to you assembled. One is factory IQC. So the counterpart to don't trust your vendor's outgoing quality is you should do your own incoming quality. That probably doesn't mean, whatever. I don't know what you're building. So that probably doesn't mean check every unit. Maybe it does. Probably it means spot check things. If you're building like, I don't know, a car, you want to make sure that, and you're buying the engine from someone, boy, you want to make sure that every single one of those engines works. So like, grade based on severity. And then there's functional test, or FATP, which may stand for final assembly test and pack out, or something close to that. Everyone has their own version of the same definition. So these happen in different places. So incoming quality happens like as soon as you get the boxes from the shipper, because you want to reject them immediately if they're bad. In-circuit test happens as soon as you get your PCBAs. Maybe those come from your factory, maybe they don't. Final assembly or the functional test and stuff usually happens at the end. So there's like a few places. So then the question is like, why do we test here and not here, or here, or here after the logistics? So there's like multiple different kinds of testing you can do. There's like design verification, and there's like manufacturing verification. The point of factory test is manufacturing verification, whatever that's actually called. It's not design verification. You do the design verification before you get to the factory as you're ramping up at the factory. By the time there's a manufacturing line building a bunch of your widget, hopefully you've figured out that your design does or does not work. So the point of these tests isn't like, can the op amp ever theoretically hit these whatever? It's like, did these voltage rails turn on? It's sort of like fundamentally a different kind of testing. I guess the other principle is you want to test as early as you possibly can, because if you don't test at all, it will be tested at the end when your customer takes it out of the box and plugs it in. So the earlier you can catch problems, the easier it is to fix them, and the less money you've probably wasted on time and on parts which maybe you now have to scrap. So these are like as early in the flow as you can test those things. Like you can't test the assembled circuit board until you have the assembled circuit board. Other tests involved in that aside. Okay, so I keep saying test. So what is test? So again, a factory is a machine. A factory is a machine that runs a process. It runs the same process. So the way that you test usually is you build a tool or a little machine for the bigger machine to operate. Often that looks like this. This is sort of what the ones I'm about to talk about look like. They can look like lots of other things. They can look like literally anything. The factory will do whatever you want, as long as they'll ask you, quote it, and they'll give you a price, and then they'll do whatever you want. Probably your test stuff will look like this and not like ponies or whatever, unless you're testing a horse bridle. Okay, so let's talk about test fixtures. So these are both test fixtures. Mike Choi is intimately familiar with these test fixtures. They look somewhat different. So this is a test fixture. The actual thing that's a test fixture here is there's a micro USB cable sitting on this table. That's the whole is like a computer with a micro USB cable. That's the whole test fixture. This fixture is attached to a computer that's off screen and a barcode scanner and a bunch of other stuff. It's this, we're going to see some more detailed pictures of this, but it's this like box in the terrible medical beige with like this big thing on top that like clamps and makes good satisfying noises and has like buttons and all sorts of stuff. But these are both test fixtures. They're a tool designed for a purpose, so they look very different because they serve different purposes. They sit in different places in the manufacturing line. So this is Mike again. So the goals of a test fixture, ensure that the thing, whatever the thing is you're testing, meets the standard, and then facilitate testing for that standard. Sometimes the thing inside is called a device under test, DUT, or a unit under test, a UUT, or whatever. They have a bunch of names. So there are some other traits you want your test fixtures to have. You want them to be absolutely reliable. Absolutely reliable. And when they fail, you want to know that they failed, and you want them to fail very loudly, because if your fixture isn't reliable, the quality of the goods you're producing is only as good as the quality of the fixture that's producing them. So if your fixture fails and you don't know it failed, someone's going to know. Hopefully, it will be you later down the line, and then you'll just have wasted money. Hopefully, it will not be your customer receiving a failed object, because you're going to spend a lot more money and you're going to spend a lot more goodwill if you catch it there. So you want your test fixtures to be reliable or loud when they fail. You want them to be low cost. There's a bunch of different versions of low cost, and we'll dive into this more soon. Most things at the factory, cost sort of looks like time. There's a bunch of different ways you can phrase cost. So you want your factory to produce 5 units a week, say. So that will take some number of humans, which will cost money, and it'll take some amount of floor space, which will cost money, and it'll require management support from the factory and things like that. So if your line runs fast, maybe you only need 1 line. If your line runs slow, maybe you need 5 lines, and each line produces 1 thing a week to get your 5 things a week. So low cost ideally means fast, or as fast as you can responsibly make it. You want them to be ergonomic. These are, most of the time, your fixture will have to be used by a human. Maybe not the whole time. Maybe it's very simple. Maybe it's just open and close. But it will be used by a human. And there's an incentive misalignment where it appears to be aligned because you want to produce a lot of units, and the human who's operating the fixture, typically called an operator, wants to produce a lot of units. But you want to produce units which are good. The operator wants to produce units. And they produce units by like doing their job. They're not, and again, it should be very clear. Like, I guess the guiding light here is don't be an asshole. And it's a mistake to assume that operators are dumb or don't know what they're doing or don't have any experience, or like those assumptions are wrong, but they have a job to do and they're going to do that job and they're going to do it any way they can. And anything you do to make their job harder is probably your fault, and they're going to do anything they can do to work around it. So if that means not testing your product correctly, but in a way that passes, they're going to do that because they're trying to build as many units as they can. So you should make it ergonomic for the users who will be using it. And then sort of a sub-bullet of point 1, you want them to be remotely debuggable. Really, it should have been a sub-bullet, or maybe not on the slide at all. But in the case that your fixture fails, if it's down the road in San Jose, say, you can like get in your car and drive for an hour and go and inspect it in person. Great. If your fixture is in, say, Asia, and you don't live in Asia, then you're going to have to get on a long, expensive plane flight, and the line will be down while you're in the air, and then you're going to have to fix it on the ground. So the more telemetry of any sort, again, you define the whole thing. It can do anything you want. It can record videos and like email you videos. That's fine. But the more telemetry it emits, the easier your job is going to be when you made a mistake and you need to fix it. Because again, anytime the line is down, you're still paying for those people. You're still paying for that space. Like, money is going out the drain. So anything you can do to make that not happen is great. So when you're designing test fixtures, there's like a bunch of constraints. Some of these are probably obvious at this point. Cycle time and cost I just talked about kind of looks like how long it takes to execute a test, or how many times the test needs to be run if it's not reliable, and things like that. There's a constant tug between how much to test. In an ideal world, you would test literally every component of literally everything, because that's how you would ensure perfect quality, right? Is by testing every aspect of every component of every part of your product. And that would totally work. Absolutely. But that's going to be long and slow, and that's going to take a really long time for you to develop. So those are bad things. So there's like a tug between how much it should test and be likely to catch things that are going to fail, and how much you let go and you hope won't be a problem. And then there's development time. I will hammer this home later, but a test fixture is a product. You didn't think that you were building another product when you decided to build widget deluxe, but a test fixture is a product. So the more time you spend, it deserves as much respect or fear in that regard as your primary widget does. And the less you predict that, the worse it will be. So there's a balance between how much time you spend developing your test fixture and how much time you spend developing your product, because those aren't, like, it's one or the, per one person, it's probably one or the other. Test fixtures have a bunch of different outputs. I still don't know what ERP is. Enterprise resource planning, that man knows what ERP is. That's also the man who's using Cadence. Yeah. The only, yeah. I wouldn't have made that distinction, but I appreciate that you did. So test fixtures have a whole bunch of different outputs. Maybe the most important is also the most obvious, which is which units passed and which units failed. Like, literally the point of the test fixture is to tell you that. There are lots of different ways it can do that. It needs to tell the operator, which probably looks like a light or a screen with words on. Oh, interesting comment. Red and green lights for pass fail, awesome, unless your operators are colorblind. Then it's not awesome. So consider using words also, because they can probably read even if they can't discriminate between red and green reliably. Yeah, and that's another, yeah, what languages they speak is a different form of ergonomics that you need to be aware of also, and dependent on your locale. So logs are kind of, to my endless horror, kind of what test fixture output really looks like. So one kind of log is that like net summary of which units passed and failed. That often comes out in a few different ways. One is like literally just a tabulated log file of like this serial number passed, this serial number failed. Another is, and this is a place where small factories and big factories differ. The factory may have some sort of resource tracking, production tracking system. If they do, it's probably better for everyone if you integrate with it. And that's sort of what I mean by the factory, PLM, ERP, work tracking, whatever. That's easy or hard depending on the factory you're dealing with. I've set up lines where we set up all of our stations and we came back a week later and the factory had put had literally placed one PC next to every single one of our test stations, and that PC was the PC to integrate with their system because we couldn't do it. So that meant that every time an operator did anything, they like passed or failed a board, then they would have to go and manually run it through this like that sucks for everyone. That's going to be a source of error. It's going to slow down your line. It's going to make your operators angry. Like, don't, if you can, integrate with their system. The other kind of log file that you will commonly want to produce is the one that facilitates that remote debugging thing I mentioned. So that's like detailed logs. I have a sample that we'll get to in a second, but a lot of the test tools that I built are Python. Fundamentally what the program looks like that's running is one outer loop with a, it's not a try catch, what is it in Python, except, try except. So what the outermost part of that program looks like is a loop, and inside that loop is a try except, and the try except catches exception, and it logs it, because when something goes terribly wrong and no other part of your software is able to catch it, you want that exception, because that's what you're going to have to look at, maybe what you're going to have to look at on the other side of the planet to figure out what went wrong in your code. So any amount of remote telemetry it can emit, even if it's like a totally superfluous amount, is worth doing, at least for a while. You can always turn it down, you can always throw the logs away, whatever, but anything you can emit will make your life easier. Test fixtures can emit calibration files. I don't know, I've never worked on anything that needed to, but I guess you could do that. Sometimes test fixtures will emit like serialization, pairing type things, scans of all the barcodes or scans of the serial numbers for the things that have paired, so you can put them in your back end and mark them as active, and I don't know, stuff like that. The other thing that you want this to facilitate is backtracing failed units. So when a unit fails, you're going to want to know why. And if you're standing there and you test it and it fails, then you can like pick it up and look at it and maybe figure it out. But if it's happening at functional test at the very end, or it was a field failure, it's really, really great to be able to go dredge through however many logs you need to and trace its serial numbers and its individual subcomponents back through their whole testing regime to figure out, oh, like it failed in the field because, I don't know, the sensor went out of bounds, and you can like go all the way back to the initial in-circuit testing and you go like, oh, it was really close to the test failure, like the failure boundaries of the test way back in the beginning, and we didn't know it should have failed, so we let it out into the field and then it failed for real. So being able to trace things like that sometimes lets you adjust your test limits and do other sorts of sanity checks. Summary logs are pretty dumb, right? This is like timestamp, serial number, and then did it pass, and then did it pass each of the various subtests. It's pretty much exactly what you'd imagine. Detailed logs, so there's a lot more metadata here. So these are the same sorts of tests, right? This is like check the voltage for this control, and then like the DAC on the test fixture measured the voltage, and it was this, and that percent error is this, and I don't know. It's like log as much data as you can is sort of the point. Again, if it's not obvious yet, like test fixtures are a product. They are hard to build well. I've never built one well. I've built them sufficiently. So it's like easy to underestimate them, but don't underestimate them. Yeah?
Go back 2 slides. That's bad for another reason. You can see there's a couple of falses in the left column, but they're hard to pick out from the truths.
Oh, yeah. Yeah. So something like this really isn't meant to be consumed by a human. Really, it gets funneled into a tool, so it's a CSV file. So really, it gets funneled into a tool which is going to aggregate the passes and the fails or something like that. Because you're right, like this is ergonomically bad for the engineer who's going to need to try to figure out what worked and what didn't. Yeah, that's a great point. I guess that's the other, like wrap your tools in more tools, I guess. So, okay, in-circuit test. This is the one that looks like the big clampy thing usually. Okay, so the goal of in-circuit test is, has this unit been electrically assembled correctly, and does it seem to work? So, you would be surprised how unreliable making circuit, and all of these things with gradations, right? Making circuit boards at volume is super reliable, usually, unless you're doing anything exotic. I've worked on products with really complicated, like, rigid flex, and everything was totally fine except for that one 6-ball BGA, which 10% of the time it would look fine, and then you'd brush your finger across it and the part would just fly off the board because it wasn't actually soldered. And like no amount of cajoling the manufacturer could get them to fix that. So you want to test things like that. You want to be able to test that, like in the case where you have an analog line and it runs through a voltage divider, you want to make sure those resistors are correct. You want to make sure your capacitors are capacitors and not resistors, because they might fit in the same place, but your board may not behave in the same way. Or worse, it will behave correctly and it'll just draw 10 times as much power for a reason you will never know. So in some sense, it's like literally an engineer with a multimeter +1. If it is a microcontroller, you want to confirm that it programs. So these fixtures can look like all sorts of things. This is the fixture which never worked, which I will pretend worked, which I built for the DEF CON badges I built last year. So this was built to test about 500 pieces. Definitely not worth contracting the great guy that we use to build the big medical looking fixtures, because that's a lot of money and I wasn't going to test that many, and it was going to be me, the engineer, operating them, so I didn't care about like the quality of the user feedback. So there's this board that I made, again, boards from China, so cheap, sorry, I love Osh Park. So there's this board which plugs into an ST-Link, and it has a serial header which is hidden over here, and it hits a bunch of test points. There's another view of those in a second, and it hits the programming header and the serial header and everything. Sort of a one-stop shop. Once everything is plugged in, it powers the board, so you don't need to put batteries in, you don't need to play with power switches. It like forcibly powers the board. This one breaks some of the test points out so you can hit them, and then it actually has, this version didn't have LEDs. One of the versions had LEDs and buttons, so you can sort of like run tests, and it has the spring pogo pins. So pogo pins are cool. I'm guessing people are broadly familiar. If you aren't, they're, in my experience, always gold. Little spears. Most of them look sort of like little spears. They're kind of hard to see. They're spring-loaded, so you put your circuit board on top and you press down a little bit and they make contact, and then they internally have a spring and everything, so you solder or wire wrap or socket onto the bottom, and then they make contact with your board. So I guess this is the mating pair. So that's the board again, and then you can see on this side there are a bunch of these little test points which hit different lines and things. The rule I followed in this case was break out basically everything I could conceivably need, and then I can choose later whether or not I needed to actually hit it with a pogo pin and test it. But you can kind of see, it's hard to tell, but this like flips over and mates. It's also worth noting on the bottom here, those pogos, the head size is such that they can hit these through-hole headers. So I never had to solder the headers in. I just plugged them in, and anyway, yeah. So like that's pretty obvious. This is the somewhat more advanced version. This is the inside of that flippy closey thing. This is the like rigid flex thing that goes in it. This is kind of what such a thing would look like underneath. Again, this is like it has a bunch of pogo pins. You put the thing in, you close it. The other interesting thing about this fixture is it's hard to see. There's kind of some like pegs and stuff sticking out up there. So this has 2 buttons and a button and then a big capacitive slider. So there are buttons that reach through the top lid. So the operator, when prompted, it'll say like press button 1, and there's a label that says button 1, and the operator presses it, and the peg is spring loaded, and it hits a button, so they can like facilitate the operator testing it. Yeah, so that works. This guy works pretty well. This is what it looks like attached to the whole system. There was not a password written on a post-it note here. So this is its test PC. It's plugged into the thing. It's a USB device. Oh, here we go. Here's a better angle, so you can see the like hand slider thing, the buttons and stuff like that. Okay, cool. So we kind of talked through it. Test points on everything you could possibly need, and then pogo pins. And you can see on this the guy who builds these for us wire wraps them. He's awesome. So he milled the top deck with a bunch of these holes to press fit pogos in, and then wire wrap the pogos to all the different devices. Typically, a fixture like this has a few pretty normal looking constituent parts. Is a PC. There's the fixture. The fixture may include a bunch of stuff, like in this case, an FTDI to hit serial lines, a programmer. This is broken out of its shell, but it's a normal SWD programmer wired into the pogo pins. Often, if you need to test analog lines and stuff, maybe you have a data acquisition box. I've used LabJacks a bunch, whatever, it doesn't matter. You can use an Arduino, it's all fine. But something that can, basically read and write analog and digital voltages. It's convenient if everything is all in the box. It's more convenient if it's all in the box and all the USB hubs and everything are in the box, and then the only thing exposed on the back is one USB connector. In this case, you can see there are 2, and we had to label them because it was never obvious what to plug in where. You want as much control as you can possibly get, because at a certain point, things become not as reliable as you expect. So, and this is kind of where you can get really far using hobbyist grade stuff, and sometimes, not always, but sometimes you'll discover like this device stops enumerating over USB after testing 50,000 units because it was never designed for 50,000 cycles, because ST, when they made my ST-Link, that wasn't part of the like hobbyist design criteria. So there's like some places where you may discover that you want to spend for things like that. One of the ways to work around it is by having as much control as you can. So for instance, you want to be able to pull power to the board completely, because sometimes things will end up in weird states. You want to reset everything before you run a test cycle. You want to totally pull power from everything. Having control over that is really good. If you don't have that control later, if you need to add that feature, you can't without retrofitting your fixtures. Board level power is nice. I mentioned earlier stuffing a resistor in place of a capacitor. For instance, a decoupling cap, depending on the size of the resistor you stuff there. It may not matter that you stuffed a resistor. The board may just work fine, but if you can measure board level power, then you can put error bars on that. And if your board mysteriously exceeds the error bars, then you know that there's like a manufacturing defect with this board. So that's a really handy metric to be able to collect. The coolest tool for doing this is not especially cheap, though I think there's one that's about to hit crowd supply made by someone who was at SuperCon. That'll make it a little cheaper. You can get controlled USB hubs, basically. So Acroname makes a 4-port USB 2 one that I've used a few times, which is totally fine. So basically, it's a USB hub with an API. So in the case of this one, it lets you measure per port power and then enable and disable power and data independently per port. So the way we used it was we hooked like the programmer and the FTDI and stuff up to some of these ports, even through hubs up through some of these ports. So before starting a test cycle, we would disconnect the USB devices from the computer and then plug them back into the computer and let them re-enumerate, because being able to do things like that lets you totally reset. If your fixture gets totally hosed, if you get caught in that outermost like catch generic exception block and something has gone terribly wrong, you want the fixture to be able to totally reset itself. You don't want the line to go down. You don't want the operators to have to like randomly plug and unplug things from your fixture, because that's what they will absolutely do to try to get it to work again, which is reasonable from their perspective, but probably not what you want. Usually ICT, usually is maybe not fair. Often ICT is facilitated by sort of a test firmware. It's your device. You can do whatever you want with it. There's no reason. You can flash customer firmware whenever you want to, which means that you can flash non-customer firmware earlier. So test firmware is super helpful. I should have put a photo here to make this a more interesting slide. Facilitates running tests on the device. So if you want to test the SPI peripheral on your device, and you can hit it with a SPI interface from the outside and then run test firmware on the device. So you send it a serial command that says run test 1, and then you send a SPI transfer, and you wait for it to come back and say yeah, I got the data. You can do things like that. That's cool. Doesn't need to be user shipping. You can make it user shipping. You can do whatever you want. I mean, if you can still OTA it, then who cares if it's user shipping? Sometimes test firmware includes information that you don't want to expose to a customer, though. It may access one-time programmable flash or things like that, or serialization things that is code you don't want to ever be accessible from the main firmware image. So you may or may not want to ship it to a customer. There's sort of different levels of autonomy. You can make it totally autonomous, where you apply power and it just runs all the tests and then gives you a green light or sends a serial message. You can make it totally remote controlled from the main PC, where you have to do run test 1 and tell the operator press the button, and you wait for it to come back and say test 1 completed. Run test 2, and it'll run test 2 and come back to you. In my experience, usually I find it's easier to develop the test station software than the test firmware. So usually I put as much smarts in the test station software and less smarts in the firmware because it's easier to update. So the other kind of testing, functional test. The goal of functional test is, does this finished product work? So this is usually the last test before it goes out the door. So you're testing finished goods. So that's why this test station is a micro USB cable, because this product that we were building, effectively the only exposed interface is USB. So you plugged it in exactly the way a user would, and it's running it was running production firmware at this point, and then it ran a series of tests by enabling and disabling different features and having the operator act like a user. Usually it's the last test before the customer gets the device. You can do a bunch of different things. You can do final backend pairing depending on the kind of widget you're making, especially if you have a limited number of serial numbers, or you have some one-time programmable flash or something. You don't want to use those up or burn those resources until you're sure the thing works. So you want to write those at the very end of the process when you're sure the thing works. You can use to flash the Golden Master real production firmware in case you had different versions of test firmware on it. Usually, if you care about locking debugging interfaces, I guess maybe not usually that happens here. That can happen here. Sometimes it happens earlier, whatever. If you have batteries and you have a PMIC or something that lets you use a ship mode or something, this is often the time that the final step for this particular product, the final step of the process was the operator putting it into ship mode and then putting it in a box, and then it got shipped to a warehouse. So ship mode is the ultra low power, pull power from the whole system type thing. It's the equivalent of the little plastic tape that you find in your coin cells and your old toys. So the goal, kind of the thing that you're really testing for FATP is stuff that's changed since the last time whatever was tested. And that kind of lets you, again, in a perfect world, you would test literally everything, but in reality, you can never do that. You test a subset. The subset you test is usually the stuff that's high risk, the stuff that's changed. So these are 3 snippets of one board. Sorry, I tried to obscure what it was a little bit. So these are examples of things that we tested on this product in functional test. So this was a board. It's a pretty big board. It goes in a big plastic enclosure with a bunch of screws. So we're using this little cell radio daughter card, which is pretty cool, and it works really well. It's a daughter card. It plugs into headers, so you can't actually pull it out. But the one thing it doesn't do is run the RF lines to the antenna. So the antenna is actually just past the top of this frame. So the way that we work around that, the way that we deal with it, is by including this really adorable, tiny little RF coax pigtail. And it works totally fine, but it's really easy to crush the U.FL, micro U.F., whatever it's called, connector. It's really easy to place it and have it canted so it doesn't actually make a connection. And then you take this whole thing and you put it in the enclosure and you tighten the enclosure, and this is on the underside of the board. So even when you open the enclosure, you can't see it. So it's really easy when you close it to catch on that one last time and pull it off, and you don't know if that happened until the device gets into the field. In the case of this device, if it had gotten into the field with that detached, that would mean that the customer was basically wasting money, because the device would disappear if the cell radio never got sufficient signal strength to actually connect. So we test that. it has a SIM card on it. The SIM card is in a push-push slot, which means that you push the SIM card in and it locks. You push the SIM card in again and it spring ejects. Great for a human, but again, we're taking this whole thing and we're putting it in an enclosure and it's on the bottom. And if you bump the SIM card as it's going into the enclosure and the SIM card ejects, you can't see that. You can't even hear it rattle because it's partially constrained. So the only way to check that is, in this case, a functional test which tries to read stuff from the SIM card. If the SIM card is ejected, you would know because it wouldn't work. It also has these, like, it has a wire harness that comes out the bottom, which is really tight. And if you pull on it wrong, the wire harness can come off or destroy the connector. So we like actuate, we do things that check to make sure that the signals running through the harness work correctly. I already told you this, I guess. This is what the FATP fixture looks like. Barcode scanners are important. Software for these things can look like almost anything. I realize I only have one random slide on it. I've done GUIs and like TK with Python, which was basically awful. I've done these like DOS style command line things. This is okay. The operators don't care. You want it to be clear. You want it to be easy to use, but that doesn't mean it needs to look pretty. I mean, it is a tool, and that's fine. Okay, so now just a bunch of random fixture tips. So everything ends up being a balance between the cost for the fixture and the development time of the fixture and the cycle time of the fixture and the reliability of the fixture and all that. So there's like a spectrum here. The engineer in me, and I would guess the engineer in some of you, is like, oh, we want to test the thing. We can test it automatically. You can test the whole thing automatically. You want to like, I don't know, what's out here? We want to test that jump bike works? Great. So we put the jump bike, we put a fake human robot on the jump bike, and we put the jump bike in a chamber with a fake treadmill road, and we like turn the road on, and we have the human pump the, like, yeah, you can do that. You can do that for anything. You can automatically test every part of every product, but there's a spectrum of complexity where it doesn't make sense anymore. So remember, no matter what, you're going to have a human, unless you have some incredible line that I've never even heard of where you have like KUKA multi-axis robotic arms taking the things out. Like you have a human who's putting it in and out of the fixture. It's fine to rely on the human to do things. They are reliable as long as they're well constrained. Like that's their job, is to be able to do things. So there's a balance between how much you automate and how much you don't automate. In a perfect world, it would all be automatic and it'd be instant and there'd be no errors because there'd be no humans. And that'd be great, but we don't live in that world. So LEDs are a really good, succinct example. So RGB LEDs are common. In the case of that weird small board thing I had on screen earlier, it has a normal like 4-pin 0606 style LED. Great. The LED is pretty important, so we actually test to make sure that all 4 legs are soldered, which means that we light each channel individually, and then we light all of them at once to make sure there isn't some horrifying error that we've never seen. You can test that an RGB LED works in a bunch of ways. You can point a color sensor at it and turn each channel on and measure the color output. And if you were going to calibrate it, for instance, you might actually want to do that. That would work. You can point any photo sensor at it and turn a channel on and just see if you got any intensity, any signal on the photo sensor, which would prove that the channel worked. Fine. You could measure total board power consumption if the noise was small enough, basically, and sense that the power consumption of the whole board increased when you turn on a channel. That would be fine. Or you can have the operator go, is it red now? Yes. Is it green now? Yes. Is it blue now? Yes. One of those things requires you to write 5 minutes of like prompts in your like terrible little command line tool, and then it's done. Photosensor ones, maybe for a certain quantity, if you really care about color, maybe that makes sense. I've never been in a situation where that made sense. I've always relied on operators. That's true of a bunch of different components of things like this, like the buttons and the slides and stuff. Yeah, you could put little like pneumatic actuators and stuff. Pneumatics are weirdly common for this stuff. You put little like pneumatic actuators on there, like push the buttons. That would totally work. Or you can just ask the operator to do it, and that's fine for the stuff that I've worked on. Granularity. Yeah, I guess the more, with all the logging and the remote debugging stuff from earlier, the more granularity you have, the easier it's going to be to debug. If you have an error message that just says the cell modem doesn't work, that's fine, but maybe the cell modem didn't work because the vendor shipped you the wrong version, which means you don't need to necessarily scrap it. Maybe you can fix it, depending on how much you care. You can also call the vendor and say you shipped us the wrong part. More granularity is usually good. More granularity also sometimes means more development time. You should serialize everything. Sometimes you build a product and the final thing doesn't have a serial number on it. That's fine. But as previously mentioned, when you want to be able to go back and find the pedigree of any arbitrary object, the way you do that is by serializing it, because otherwise you can't tell this one board from this other board. You want to do it as early as you can. I've definitely been in situations where we've had boards fail, but they failed before they got to the point where we gave them serial numbers. And then usually we use names. So it'll be like Steve, and the one that gets really hot, which we call hothead, and like stuff like that. So serialize as early as you can. Serialize ideally with like a barcode. Usually you can ask your whoever's making your PCBAs or the people taking the boards into the factory, you can ask them to put a little like serialization barcode thing on there, and they'll totally do it. You just need to know to do that. Yeah, those are the reasons, because you also can't track your work in progress as, you like test the thing and it goes in a tray, and you take the tray and you move it over here and you take it off the tray and you test it again. That's all fine. It's easy to accidentally mix things up, and if your boards have all been serialized, then maybe you can tell if the tray has been tested. If they haven't been serialized, good luck. Test it all again, because you have no idea, and that's the only way to be sure. More random fixture things. Fast and easy as possible. Again, so this is the operator thing. If you have serial numbers, don't make them type them in. That will be error prone and very slow, and it will make them angry. In fact, they will probably not do it. They will do it while you're there, and then you'll leave, and they will take a barcode scanner from someone else's line, and they will plug it into your computer, and they will just do whatever they want. Because this is, again, like if you had to type a 20-digit number in 800 times a day, you wouldn't like that either, so why would they like it? Like, make it as easy as fast as possible. Get a barcode scanner. Make the barcode scanner like scan automatically. Make it scan automatically and hit enter automatically, so they just wave the board under it, and it beeps, and that's it. It's done. Great. As automatic, smooth as possible. Make everything impossible to do wrong. I guess the thing that I've observed is that eventually someone will do every possible thing with every part of your tools that you can imagine, and many things you can't. Like, they'll try every combination of plugging and unplugging different ports. They'll put your board in upside down. They'll put your board in at 90. If you have a square board and it has a hole in each corner and all the holes are the same size, great. You can put that board in 8 configurations, all 4 cardinal directions. Then you can flip it over and put it in all 4 cardinal directions again. Like, if something doesn't prevent them from doing that, eventually something will fail, and they'll go, maybe I got it wrong, and they'll try each one of those combinations. So make it, in the case of the 4-corner board, make your holes like asymmetrical, so you can't do that. Make it so the fixture doesn't close. The test won't start if the fixture isn't closed, if the thing isn't engaged. Make everything as hard to screw up as possible. The barcode's cut off. If your barcode scanner isn't configured properly, or something is weird and a barcode gets scanned twice, great. You don't want to accept that barcode, because the barcode, when you run it through the rest of your automated tools, the barcode's going to be twice as long as it should be, or missing a character. Like, make it so that, for instance, if your barcode follows a simple or a single format, you check the length, you check the format, so they didn't scan a random barcode, because again, if the barcode scanner isn't working reliably, but it works reliably on that one, and they need to make 300 more units in the next hour, like, who knows what's going to happen? Maybe they'll end up typing random things in. Maybe they'll scan the same unit again and again and again and again. Like, their job is to build units. If that makes it easier, and yeah. Barcode scanners are really like a thing. You see, they come up in all these lines. The first thing you'll do, so you'll like realize, oh, we should have barcode scanner. And you'll go to Amazon, and you'll go barcode scanner, and you go $25, pretty good reviews. I buy it. You buy it. It's going to work terribly. You won't care, because you're building 3 and you're just testing the thing, and that's fine. But then you'll get to the really tiny barcodes on your PCBAs, and the barcode scanner will take 1, 2, 3, 4, 5, beep, 6 tries to work, and it'll take forever. And you'll sit there and you'll watch, and your operators will do it, and then you'll leave, and then they'll unplug your barcode scanner, and they'll walk to someone else's line, and they'll get the super nice $300 Zebra scanner, and they're going to plug it into your line, and they're going to use that instead, because holy shit, a good barcode scanner works so well. You get like the crazy, like 2D, 3D, whatever, you point any orientation, any direction, any distance, tiniest QR code, like a good barcode scanner. This is actually probably a product opportunity. A good barcode scanner is a fucking good tool. A bad barcode scanner will make you want to kill yourself with the barcode scanner. Like, so in terms of things where it's worth paying for good gear, buy good barcode scanners, because your operators won't care if you don't. They will fix it, and the way that they'll fix it is by getting another one. And barcode scanners, usually you can configure to like hit enter or hit tab or add characters, whatever. When they unplug one from another line and they plug it into your line, it's going to do the wrong thing. So, for instance, when that happens, your tool needs to detect it, because then they'll just use it. And if it like hits tab but it needs to hit enter, and like, so I had a tool where we had crappy barcode scanners, and to like complete the text box you needed to hit, you needed like a carriage return or something. But if you used a line feed, it would clear the text box, because it would scroll up. So what we had was operators would scan they like plugged a random barcode scanner in because we were idiots and we got bad barcode scanners, and they'd scan it, and then they'd see it in the field for a second, and then it would disappear. So they'd like scan it a few times, and eventually a character would drop or something, and it would stay in the thing, and it'd enter, and you'd get like, either you would get like 6 barcode scans, or you'd get 1 barcode scan, or they'd hit backspace because that made it come back. So so they hit backspace twice, great, you don't have a serial number anymore because they just deleted a character from your barcode. Like, all of these things need to be protected against as many, defense in depth, as many layers of protection as you possibly can. And then the neat trick I discovered was you can ask the factory what barcode scanners they use, and then you can buy them from the factory, and they'll just source them however they source them, and then you'll get exactly the same ones everyone else has, and they'll work really well. And then you label every single one with your line name, and you label every single port on the other side with what goes in there and whose barcode scanner, and then you ask, oh, it's not working, great. Are you using our barcode scanner? Like, did you plug it into the port that says it goes for our barcode scanner? Great. You didn't do that? Okay, fix it. Oh, that barcode scanner with our name ended up on that line? Great. Bring it back. It needs to stay with our line. Plug it into the port. Like, as much of this as you can regulate as you can. Okay, so obviously, there are a bunch of things there. So the 2 takeaways, the 3 takeaways are buy good barcode scanners because, boy, they're awesome. The second takeaway is that factories are like weird to deal with, so hopefully maybe this is helpful. Test fixtures are a product, so don't underestimate how hard it's going to be to get the test fixture right. You can probably take it to the factory and like demo your fixture for operators and get them to use it and stuff. That's super helpful. What's also helpful is setting it up in a conference room and getting a random coworker to come and use the test station, because then you'll have to train another human who has no familiarity with it how to use it, and you can sit and watch and go, wow, they just can't figure out how to use this control. You should consider fixing that. Right, so like quality is only good as the tests for the tools, and then the tests the tools are running for your thing. So don't let your customer be your FATP test by writing really bad tests or no tests, and testing is hard. Okay, cool. This has been a small sane manufacturing test. Please pick 3. Oh, and if you have any questions, oh, well, actually, I guess, sorry, I'm supposed to stand here and do questions. Yes, Nick.
So I'm thinking, having watched all that, it seems to me, and I'd like to get your thoughts on this, it seems to me like any of the Raspberry Pis might be a great foundation for
Yep.
test tools.
Yep. I've used Nux a bunch because it's convenient to have. Sometimes you want a Windows system, so whatever. Yeah, Raspberry Pis work great. I have not used one. I know a bunch of people who have. Awesome solution. Cheap, easy to deploy. Buy them by the 10. Right. Super easy. You don't you could use a microcontroller to do pretty much any of those tests, and that would work totally fine. But you're going to want to plug it into a network, and you're going to want to be able to write software for it conveniently. And boy, it's really great when you can write Python on your laptop and then just push the files to the Pi.
Mail you the files every day.
Yep. Totally works. Great solution. Yeah.
I have just one comment about serialization. So obviously I worked with Kerry on that product, and serialization, although it's an incredible tool for debugging and many other reasons, it's a very much a double-edged sword depending on the other aspects of your assembly. For instance, all the drama with the barcode scanners, there's a step in that test where basically it's a point of no return. Once you write that serial number, it's unrewritable. And so for whatever reason, they picked the wrong barcode scanner out of the wrong barcode out of the bucket of barcodes. Like it's something that you can't return from.
Yeah, so I think the thing you're referring to is that product has the serial number is written in 3 places. One inside the micro in some flash that we can rewrite, one inside the USB to serial bridge, which you can only write once, and then once it's laser etched on a piece of plastic, which is glued onto the assembly. But it's only glued onto the assembly at the very, this is a place where I think if either of us had more experience doing this, we would have come up with a better way to do it. So at the point where you, so we get those laser marked pieces of plastic from the vendor that does the laser marking, and they have a sticker on the end with the serial number and a barcode. So what the test looks like at the very end of ICT is the operator, if it's passed everything up till then, the operator scans the barcode, and then it sends it to the micro, and the micro writes it in the 2 places, and then they have to keep that board and that plastic marked piece together forever. And if they ever lose the plastic marked piece, that's it. That board is scrap because you can't rewrite those fields. So it turns into like a toe tag, I guess is the term for it. I don't know. So you end up having a weird problem where you have like little plastic bins, and you like put the things in the bins. And was that the?
Yeah, it's just like very much a
Yeah. One sec.
We actually solved that one on our line by putting a Yagi laser at the end of the line.
Yeah, it works great.
It etches right onto the AVS right there from the unit while it's electrically powered, pulling the serial out.
Interesting. Okay, well that works. If you can get
The code that drives the laser is actually running on the device. What? Yeah.
that's interesting. I'm imagining these are the little SD card imps that have all the info etched on the back. Maybe they, okay.
I would have loved it.
Yeah, that would have been great. No way we could have afforded that.
We did the laser in China, we did the assembly in Fremont, so that would be difficult.
Yeah.
At a price.
Yeah.
One good solution to that is some of the micros that might be part of a product have, if you can if you can program, there actually is like a wafer ID
Yeah.
serial
Yeah.
and guaranteed unique string in there that you could actually get out. And
Yeah.
well, I'm going to pinch that and have that be the serial number.
Yeah, so I've used that before, and that works super well. Or you can run that through like a hash or something if you need different. Yeah, the one caveat that I accidentally discovered once was that it was unique down to 10 because there'd be like 10 wafers in a stack that were all processed in the same batch, and so all of the chips would have the same XY and the same date code and the same batch code, but it was 10 wafers at once, so there would be 10 parts in the world instead of 1 parts in the world.
Go back to the vendor and say,
Yeah, this is bad. Yeah, do better. Yeah, yeah, that totally works.
Does anyone apply statistical process control at this scale?
I have never been involved in a program that did. I've actually, honestly, I'm not sure I've ever, on any product, even backtraced a unit through it. It's something we've talked about doing a bunch of times, and it's like obviously a goal. But so I've never been involved in anything that did.
For 200 a year, you would do it.
Right, for 200 you wouldn't do it. For 10Ks you would, right? Especially if the subcomponents were expensive and you might want to salvage them.
Or like trends.
Yeah.
And you know, if you're starting to move out of your guard bands, it gets switched.
Right, right. So
You see connector wear doing that. If you plot it, you can start to see connectors start to wear in the testing.
Yeah.
oh, that's interesting.
Yeah.
We've discovered when things were wearing by like the fixture doesn't work anymore and we don't know why, and then we buy them another bag of 50 ribbon cables and say throw those away and plug in new ones. So usually you end up getting feedback from the factory. So this is part of why you want to keep the factory in the loop with test output by plugging into their system. Is usually once you've run the line for a little while, they'll start coming to you to complain that like they're having failures and that's bad. They want to fix usually contractually, they want to fix the failures. So they'll say, we had 50 boards fail this test, why? And then you'll sit down and spot check a bunch of logs. And for the failed units, incidentally, this is why you need serials, because when they come back and they say, 50 units failed this test, but you don't have serial numbers, you don't know what logs to look at, you don't even know how to differentiate the logs from each other because they're just like logs with a timestamp, good luck. So I've definitely been in situations where the factories came back and said like 50 units failed this test, why? And then we go and look and go discover that the test limits were wrong or something like that. But that's the most elaborate I've done.
It's been a long time, so many years, but the factory shipped me the good boards, fails. Oh yeah, it's really hard to find that one.
Great.
Boards that are dried out and shipping.
Dried out?
Yeah, there was a moisture issue in the boards causing a leakage, and then they shipped them halfway around the world slowly, and they were dry by the time they arrived.
Dry meaning you couldn't reproduce the problem because they were no longer in the.
I could.
Yeah. Okay. Oh God. Ugh. Okay. Cool. Find me on Twitter at Borgle or come talk to me if you want to know more.